Alright, so this begins part 2 of lecture 9. I just want to look at how isometries act on vectors, in particular vectors like velocity vectors or acceleration vectors along a curve. So suppose alpha, alright, suppose alpha from I, and we'll do Rn. If you really look at what I did in the last part, you'll see that it just as well, I may have said R3 at some point, but honestly, no. I was careful. I did develop it for Rn. Of course, we're primarily interested in R3, but definitely we can develop these general comments for Rn. Okay, so you have a smooth parametrized curve, alpha, right? Then we defined, remember we defined the velocity alpha prime of t to be a vector, really a vector field along the curve. And to be specific, what we did was we differentiated the component functions, the Cartesian component functions of the curve. And so those give you the component functions of the vector field, right? Like so. And I suppose I should mention we can just as well calculate the derivative of the derivative, or and so forth and so on. So like the kth derivative of a vector field of a curve is also a vector field formed in sort of the obvious way. Now, of course, you could view this as a differentiation of a vector field along the curve, but I'm just going to get to the point and tell you the end result of it is just this, all right? All right. Now, if we have an isometry, right, then we can also take a look at the, let's say, f composed with alpha, right? That gives me another curve, right? And you know, if I was to call this beta just for the sake of saving some writing for a second here, we can calculate beta prime and beta prime prime and so forth and so on. I mean, if it's smooth, we can do it forever and ever, all right? So these are vector fields we can look at. Now the question then, the natural question to ask is, how are the, how are these tangent vectors related, let's say? How are the accelerations related? Are they related? How's the kth derivative related? Is it related at all? All right. I said isometry, right? But let's dial it back a second and just say, how about let's say consider G a map. All right, just a map from Rn to Rn, smooth. Okay. Maybe once differential is enough. Well, if you look at G composed with alpha prime of t, what is that? Well, by definition, sum I equals 1 to n d of the composite of G with alpha dt, and of course that's the ith component function of that, partial xi at g of alpha of t, right? And then this is the derivative of a function, of another function, calculus 3 we learned the multivariate chain rule. So what you really have here is the sum over I nj 1 to n. And so what we got is we've got partial gj, partial xi. If you want me to be really, well, fine. That's at alpha of t, right? And then, let's see here, then times d alpha I dt, and then partial xi at alpha of t. Okay, so, and you may recall, we called this the, this is really another, oh goodness. This right here is also known as the push forward at alpha of t under g. Let's say some parentheses there of alpha prime of t. Okay, so what this little calculation shows you then is if I was to take a curve alpha, right, let's take a point, say alpha of t, right, and then I was to take the image curve over here, so, and the corresponding point g of alpha of t, right, then the tangent vector, right, let's say here, alpha prime of t, all right, would get pushed forward by the map, right, let's say over to here, d alpha of t g alpha prime of t, or you could just say g push forward of alpha prime of t, if you prefer. So on the one hand, it's just, you know, the push forwards doing that, but on the other hand, if you just think of the curve g composed of alpha on its own, then it also takes that same, you know, that same tangent vector it produces just as the tangent vector, right? They agree. So that's a theorem. Okay, so you can ask, well, is the same thing going to happen for higher derivatives for just a map g? The answer is no. All right. So basically here it is, the push forward of the velocity vector field along a curve is the velocity vector field of the transformed curve. So that's my theorem 3.2.1. If you want to see it stated a little bit more carefully, the proof is right here. Now, this is not true. For alpha prime prime and so forth, unless we give, so here f is just smooth. But it's not true for more general accelerations, so forth and so on, unless we give further data about f. In particular, if f is an isometry, we'll shortly prove that it preserves what's called the k-jet. It preserves all of the derivatives in this way. Okay, so let's see here, moving along. You know, should just say a bit about notation. It seems like we're always talking about notation. What can I tell you? The push forward, right? Push forward of x. What is it equal to? Well, that's the, let me be more pedantic here for a second here. Push forward of, let's say, that would be, oh man, I forgot my sum. Sum over I of x upper I, partial xi, right? Well, that's equal to a sum over, and we can say I and j because they're both n-dimensional. Generally, you need two sums, 1 over m, 1 over n, different dimensions and stuff, but here, same dimension. And so what we have then is we have partial f j, partial x I, and you pick up the x of i's, right? And then you've got your partial xj's. Now I would usually have x's and y's in the domain in the range or the codomain, but here I'm using the same coordinates both places because of the nature of the problem we're looking at. Now, I mean, we're looking at functions from Rn to Rn, and we're identifying Rn as being the same space, okay? So it has the same coordinate system in the domain and the range. But this is all a lot to write, and really what you're boiling down to is this is the Jacobian matrix of F. And the index conventions we tend to use here, I try to use here, are that this would be, let's see, try to remember, I think that would be J, I, like that, and then X upper I, okay. You see the J is up, the I is down, okay, ha ha ha. And so, but you could also look at that as just being a matrix Jacobian times a column vector X, right? And it's the jth component of that. All right, and so in other words, if I write such a thing, well, here that's legit, but more generally, I'm basically dropping some of these, and if you see something that doesn't make sense, basically what I've done is to say that this is the standard basis, and so I'm using coordinates with respect to the standard basis in some places in what follows. The the best example of that would be if I'm making that identification, I could write this. I could write the push forward of X, right? It's just equal to the Jacobian matrix of F times X. Of course, this is an abusive notation, but it's a useful one for our purposes in this section. All right. So let's see here. Now, well, I guess I should mention, fine, whatever. In my usual linear algebra, I would just write this, the Jacobian of F, Ji. So if it's bothering you, you can always write the indices down. But anyway. Okay, so the central calculation here really is this. If I have, so suppose F is an isometry, right? That means that what? We can write, let's see what it really means is, so I'll choose a color eventually here. The ith component of F, right, at X is equal to what? It's equal to a sum, J equals 1 to M of R, upper I, lower J, X upper J, plus A upper I. And this is, of course, for some R transpose R equals to I. In other words, R is an orthogonal matrix, right? So if you were to calculate the Jacobian matrix, right, of an isometry, what do you get? Well, partial Fi, partial, let's say xk, well, that's going to be, I can bring the derivative inside the summation. These are constants, right? So the derivative goes right past those, and it just hits the coordinate function, like so, right? And this differentiates to 0. That's just a constant, it's got no x dependence. So this is what you're left with. But hey, this is our old friend, the Kronecker delta. And so what you're left with, of course, is just R. Let's see here, I and k are free. Better keep them. I and k. Alright, so what that shows you then is the Jacobian matrix of an isometry is simply the orthogonal matrix of the isometry. Alright? And so once we know that, then in view of the abusive notation I was just engaging in before this little discussion, the push forward by an isometry of a vector just amounts to multiplication of the vector by R. Of course, I'm replacing the vector with its column vector, coordinate vector with respect to the standard derivation basis on Rn. if you want me to be more pedantic. Actually, if you want me to be more pedantic, I can be. It would be something like this, right? F star push forward of the pair p comma v is equal to f of p comma rv, where rv is really just the vector part, okay? And I'm using the column vector. Sorry, maybe it'd be better if I threw in 5 isomorphisms and just was always totally explicit and made none of these identifications. I don't know. But then I'm not preparing you for the people who are similarly careless the way I'm being careless right now after you stop watching this stuff. Oh well. Anyway, so a k-jet, all right, is not just the first derivative. It's the first derivative, second derivative, third derivative, all the way out to the kth derivative at a given point, all right? And so if you have all of those together, we call that the k-jet, right? And so what we can prove then is that because of this, actually, we'll prove that the isometry naturally will transfer a k-jet in the following sense. So this is the theorem. So we got an isometry if f of x equals to rx plus a is an isometry for some r and on, right? And alpha from I to Rn is a smooth parametrized curve. Then for k in the natural numbers, we have the following. Yeah, the push forward of the velocity is the velocity of the transformed curve. The push forward of the acceleration is the acceleration of the transformed curve, and so forth. The push forward of the kth derivative is the kth derivative of the transformed curve. Right. Moreover, a little bit more than that, we also get that because this push forward is happening by this orthogonal matrix, we also get preservation of the magnitude of the ith derivative. And more interestingly, I suppose, I mean, this latter thing gives you the former, I think, right? Push forward of the dot product of the push forward of the ith derivative dotted with the push forward of the jth derivative along the curve. Subtracting is equal to the dot product of the ith and jth derivative on the curve. Now this is my theorem 3.2.2 if you can't read something I wrote right now. Alright. So, you know, what's the proof of this theorem? Well, the proof is rather simple, right? Sorry, I'm trying to get everything in frame here. So here's the proof. First of all, let's just let v equal to the kth derivative of the curve, right? And recall from our little calculation right before the theorem that the push forward acting on a vector, right, is equal to r times v. So, all right, well, I mean, that shows you what? I mean, sorry. Okay, fine. So the push forward. Sorry, I'm doing entirely too much writing here. So that's the push forward of the kth derivative, right? But also we can calculate the transformed curve, right? So f composed with alpha of t is what? It's r of alpha of t plus a for some translation, right? And when you differentiate that, what happens? If you differentiate it k times, of course, even after the first derivative, that piece vanishes. R is a constant matrix, so you're just left with r times the kth derivative at t, right? Or, in other words, that's the push forward of the kth derivative at t. All right. So there's the first part of the theorem. But we'll prove the dot product thing, all right? If we have f star, and let me just go ahead and replace alpha I of t with v and alpha j of t with w. So this, all right, dot that. I mean, it's I don't. Maybe I don't even need to. Maybe we've already done this. I mean, I'm just doing it again. So that's RV transpose really times RW, which of course is V transpose R transpose RW, but that's the identity matrix, which gives us V transpose W, which is of course V dot W. So apply this identity. To the ith and jth derivatives along alpha, and that gives you this. But if you take I equals to j, that gives you the square of this being true, which then gives you that as true as well. So it preserves the dot product between derivatives of different orders possibly, and of course the norm of each derivative. So that completes the proof. All right. Sorry, I feel like I'm spending too long in this proof, and if you feel that way too, I'm very sorry. Moving along. Let me get this out of the way. All right. Well, that's a very interesting result we have, right? Because what's that mean? Well, getting things back on track here. So if let's just go back to n equals 3 for a second here, right? If we specialize to n equals 3, then if you think about what this means, well, we had the Frenet curve, right? T, N, and B. And how are these really defined? Well, if you think about it, we had T for arc length, right? T was alpha prime, right? N was essentially proportional to the, well, sorry, N was, what was it? It was 1 over the curvature, right? And then T prime. And then you had the binormal, right? Which was the cross product of these guys. But you remember there's also a formula for the binormal in terms of the third derivative, I think. Or what's the cross product of something and something? I don't know. It slips my mind at the moment. But the point is, these are all governed by the velocity and acceleration, basically, of the curve, right? And so, if we have an isometry, and it preserves the angles between, so like an isometry push forward velocity dot the isometry push forward the acceleration, well, that's going to be the same as the acceleration dot the velocity dot the acceleration, right? For example. And so that means that the relation between t, n, and b for alpha is going to be the same as the relation between t, n, and b for, f composed with alpha. If I say beta equals f composed with alpha, then this has same relation between beta prime, etc., as alpha prime, and etc., and so forth. And so eventually we're going to give a careful proof of this, basically showing that the shape of the curve is maintained, in fact, by one of these isometries. There's something else interesting, right? There's an example in O'Neill where he shows that if you just have a smooth map, it does not preserve the acceleration. All right, so in other words, the acceleration of the the transformed curve does not match the push forward of the acceleration. But this is not, of course, the case for an isometry, right? And so if you think about Newtonian mechanics, another interesting thing to think about is, Newtonian mechanics is all based on what? I mean, the central thing to think about is force net, right, equals ma. But something we don't spend enough time talking about in physics, and we should probably spend more time, is, with respect to what system of coordinates is this done? Well, you can see that in order for this to make sense, we better allow for other coordinate systems. If we allow for other coordinate systems, there has to be some sort of regular way in which the acceleration from the new system and the old system are related, right? And it turns out the natural structure, if you want to think about all possible coordinate systems in which Newtonian mechanics have natural statements, then this brings you to the study of what are called, what are they called? What's called a Euclidean structure. Euclidean structure is some notion of physical space paired with these so-called allowed observers. Two observers are inertially related if basically there's an isometry which relates them, and it's a little bit more than that though. You also have some time involved, right? Here our orthogonal transformations have no time dependence, right? In studying Newtonian mechanics, then you have observers. You have coordinates which can move with respect to time, and that complicates things a bit. If you'd like to read more about this, you could look at my Math 430 notes. But that's about all I have to say here, except just that basically isometries are nice to acceleration. I mean, I'll just leave it there for here. It's all we really need for now. So the next lecture, I'm going to talk about Frenet curves in Rn, and so I'm going to stop here for now. Thank you.